Hello friends, I welcome you in lecture number 9 on series solutions of differential equations. In lecture number 8, we have discussed about Legendre polynomials and we have seen how we can derive Legendre polynomials from the linearly independent solutions of Lagrange equation. In this lecture, we are going to discuss general formula for Legendre polynomial of degree n. So we are not going to derive or discuss that how this formula is coming, but we will accept this formula, and using this formula we will try to write down first few Legendre polynomials. So this is the general formula for Legendre polynomial of degree n and is given by this finite summation Pnx equal to sigma r equal to 0 to capital M. In the numerator we write minus 1 raised to r 2n minus 2r factorial. In the denominator we have 2 raised to n times r factorial times n minus r factorial times n minus 2r factorial into x raised to n minus 2r. So you can remember this formula easily. We are just writing again. Legendre polynomial of degree n is given by this finite summation index we have taken as small r. R is from 0 to n. Here we write minus 1 to the power r 2n minus 2r factorial. Here I am writing 2 raised to n into r factorial into n minus r factorial into n minus 2r factorial and x raised to n minus 2r. Let me check whether I have written correctly or not. Here 2 raised to n r factorial, n minus r factorial, n minus 2r factorial. So you should remember this formula. What about this capital M? So this capital M is either n by 2 or n minus 1 by 2. So consider that value which is integer. If I have n equal to 4, then n by 2 will be equal to 2. So I will consider capital M equal to 2. If I have n equal to 5, then n by 2 is not an integer. So I will consider n minus 1 by 2, that is 5 minus 1 by 2, which is equal to 2. So capital M is n by 2 if n is even, and it is n minus 1 by 2 if n is odd. And using this general formula, we can derive first few Legendre polynomials. So we will remember this formula. Here capital M is n by 2 or n minus 1 by 2, whichever is an integer, or you can remember in this way also. Consider capital M equal to n by 2 if n is even positive integer, and if n is odd, we will consider capital M equal to n minus 1 divided by 2. So here I have determined first few Legendre polynomials using this formula. So first I am writing this formula again. Pnx is given by this formula, and now we will consider particular values of small n, and we will determine sum of the Legendre polynomials. For n equal to 0, I consider n equal to 0 everywhere here. Now if n is 0, capital M is n by 2, and if I take n equal to 0, I will have n by 2 equal to 0, which is integer. So for small n equal to 0, value of capital M will be 0. So we have to find out value of this expression for n equal to 0, and possible value of r is 0 only, because r is from 0 to m and m is 0, so possible value of r is 0. So we will consider n equal to 0, r equal to 0 in this expression, and we will see what we obtain for n equal to 0. So I have written here capital M is 0, hence r is 0, and we put n equal to 0 here, that is p0x. Here we take r equal to 0, so we have minus 1 raised to 0, n is also 0, r is also 0, so this is 0 factorial. Similarly here we have 2 raised to n, that is 2 raised to 0, r is 0, so 0 factorial. N and r both are 0, therefore we have 0 factorial into 0 factorial. And we know that 0 factorial is 1, minus 1 raised to 0 is 1, 2 raised to 0 is 1. Here also n is 0, r is 0, so we have x raised to 0. So we find out that polynomial of degree 0 is given by p0x equal to 1. Same thing we can do to obtain other Legendre polynomials. For example, now suppose I consider n equal to 1. Then I know that n equal to 1 is odd integer. So value of capital M is n equal to 1. So capital M is 0 if I take n equal to 1. And value of r will also be 0 because capital M is 0. So for n equal to 1, we will consider r equal to 0 and n equal to 1 everywhere in this expression, and we will be able to decide Legendre polynomial of degree 1. So that I have written here. For n equal to 1, capital M is, if we take n by 2, we obtain 1 by 2, which is not an integer. So we consider n minus 1 by 2, and for n equal to 1 it becomes 0. Therefore m is 0. R is from 0 to m, therefore r is also 0. And now we put r equal to 0, n equal to 1 everywhere here. So we can see r is 0, so minus 1 raised to 0, n is 1 here, and r is 0. If I take n equal to 1, I will have 2 factorial, 2 minus 0. Then n is 1, so this is 2, r is 0, we have 0 factorial, n is 1, so 1 factorial, r is 0, so again 1 factorial, into x raised to 1 minus 0, that is x. So that thing I have written here, p1x is equal to this. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, so that will cancel out with this. Minus 1 raised to 0 is 1, so we have 1 into x, that is x. Therefore p1x is equal to x. Similarly, we obtain for n equal to 2, we will obtain Legendre polynomial of degree 2. So if n is 2, we can see that n equal to 2 is even, therefore m will be equal to n by 2, n equal to 2, so m is equal to 1. And r is from 0 to m, therefore r is from 0 to 1. So we have to find out two terms of this summation, one for r equal to 0 and n equal to 2, similarly for r equal to 1 and n equal to 2. So first we determine the term of this summation corresponding to r equal to 0 and n equal to 2. Then we determine the term corresponding to r equal to 1 and n equal to 2, and we find out p2x. So first I have taken capital M equal to 1 and n equal to 2. Okay, we have this formula. Let me write again. Pnx equal to sigma r equal to 0 to m. M is 1 now, and we have minus 1 raised to r, 2n minus 2r factorial, x raised to n minus 2r divided by 2 raised to n times r factorial times n minus r factorial times n minus 2r factorial. Now here I put n equal to 2, and first I simplify this for n equal to 2. So I will have sigma r equal to 0 to 1 minus 1 raised to r. If I take n equal to 2, I have 4 minus 2r factorial, and here also I put n equal to 2, and I will get x raised to 2 minus 2r. This is 2 square, that is 4, r factorial as it is, and here we put n equal to 2, and we have 2 minus r factorial, 2 minus 2r factorial, x raised to 2 minus 2r. So first we have taken n equal to 2 in this summation, and capital M is 1, And now we determine this expression for r equal to 0 and r equal to 1, and we take their addition. If I take r equal to 0, I have 4 minus 0, that is 4 factorial, minus 1 raised to 0 is 1. If I take r equal to 0, I will have x square. Here it is 4, 0 factorial is 1. This is 2 factorial and this is also 2 factorial for r equal to 0. Then we take r equal to 1. So here I will have minus 1 raised to 1, that is minus 1. If I take r equal to 1, I will have 4 minus 2, that is 2 factorial. Here also 4 as it is, r equal to 1, that is 1 factorial. 2 minus r equal to 1, that is 1 factorial, and 2 minus 2, that is 0 factorial. And for r equal to 1, I will have x raised to 2 minus 2, that is 0. Now this I can simplify. First I rewrite 4 factorial as 4 into 3 into 2 into 1. This is 4, 2 factorial is 2, 0 factorial is 1 into x square. This negative sign is there, and 2 factorial is 2, 4 is written, 1 factorial is 1, x raised to 0 is 1. And here we can cancel out 4 and 2, and I am left with 3 by 2 x square, and this is minus 1 by 2. And we can take 1 by 2 common, and we obtain that p2x is 1 by 2 into 3x square minus 1. So remember this general formula for Legendre polynomial, and using this general formula we can decide Legendre polynomial of degree n. I have derived Legendre polynomials of degree 0, 1 and 2, and I have written Legendre polynomials of degree 3, 4 and 5 here, that we can derive by taking n equal to 3, 4 and 5 in that formula. So these are the first 5 Legendre polynomials. So sometimes they can ask you the question about Legendre polynomials, that write down the formula for Legendre polynomial of degree n, and from that formula obtain first 3 Legendre polynomials. Or sometimes they can ask you to define Legendre polynomial. So you can consider this as definition of Legendre polynomial also. You can write down definition of Legendre polynomial by this expression also, that is also valid. Another definition we have seen in previous lecture, so if you wish you can write that definition also. So remember this formula again. For recall of this formula, we are writing again the formula of Legendre polynomial of degree n is given by sigma r equal to 0 to capital M. Here I write x raised to n minus 2r minus 1 to the power r to n minus 2r factorial. Here I have n minus 2r, so here I can write n minus 2r factorial. Here I write n minus r factorial. Here I write r factorial into 2 raised to n. And capital M is n by 2 if n equal to, or if n is even integer or 0, and m equal to n minus 1 by 2 if n is odd positive integer. So remember this Legendre polynomial formula. This question was asked in GTU summer 2019 exam. Here they have asked to write Legendre polynomial of degree n and hence obtain p1x and p2x in powers of x. And we have already done this question. We have obtained p1x and p2x using that formula of Legendre polynomial of degree n. So we have already answered this question using this formula. Okay, fine. So in this lecture we have discussed general formula for Legendre polynomial of degree n, and it is given by this. So this is all about this session. I hope you like it. Thanks for